The morning of February 24, 1944, Anzio beachhead, Italy. German Junkers 88 bombers drone through the darkness, invisible against the black Mediterranean sky. American anti-aircraft gunners scan desperately for targets they cannot see, their optical rangefinders useless in the moonless night. 4 90mm guns sit silent, waiting for targets that conventional fire control cannot find. Then, a new voice cuts through the radio static. A technician hunched over a glowing radar screen 15 yards behind the gun's watches as 12 bright blips appear on his display. Range, 11,000 yards. Bearing, 035 degrees. Altitude, 8,000 feet. His fingers move across switches and dials as numbers flow automatically to the guns through electrical cables. The barrels swing and elevate without human hands touching them. The first salvo rips into the night. Shells explode precisely where the radar predicted enemy aircraft would be. 5 Junkers disintegrate in brilliant fireballs. The remaining bombers scatter and flee. Not a single American gunner had seen what they were shooting at. They had fired blind, letting machines see for them, letting electricity aim their guns, trusting mathematics and radio waves to hit targets human eyes could not find. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. German night bombing of Anzio effectively ceased that evening. Something fundamental about warfare had changed in those 60 seconds. American artillery no longer needed to see its targets to destroy them. The age of blind fire had arrived, and it would transform every battlefield from Italy to the Pacific. What made this possible was not courage or training, but 3 interconnected technologies that together solved a problem as old as artillery itself. How do you hit what you cannot see? The brutal mathematics of aerial warfare during 1942 painted a grim picture for Allied commanders. British Royal Navy destroyers fired 20,000 anti-aircraft shells to bring down a single German bomber during the Battle of Britain. American gunners at Pearl Harbor unleashed 1,400 rounds without achieving a single confirmed kill. The problem was not incompetence, it was physics. Traditional anti-aircraft gunnery required predicting where a 300-mile-per-hour aircraft would be 4 to 6 seconds into the future, setting a mechanical time fuse by hand, and hoping the aircraft maintained exactly the same course and altitude. Miss that timing calculation by 0.3 of a second, less time than a human heartbeat, and $50 worth of precision ammunition exploded uselessly in empty air, while enemy bombers continued their attack runs unmolested. The same limitation plagued naval gunnery after darkness fell. Battleship guns capable of hurling shells. 25 miles became nearly useless at night because optical rangefinders required seeing the target vessel and observing where shells splashed to correct aim. During surface actions in the Solomon Islands throughout 1942, American cruisers and destroyers fought desperate nighttime battles against Japanese forces who possessed superior optical equipment and aggressive tactics. At the Battle of Salvo Island in August 1942, Japanese searchlights and excellent night optics allowed them to savage an American task force that could barely see its attackers. The USS Quincy, Vincennes, and Astoria went to the bottom of what sailors grimly nicknamed Iron Bottom Sound. American gunnery officers understood they were fighting with a fundamental disadvantage. They could not see well enough in darkness to aim accurately, and even in daylight their anti-aircraft fire achieved hit rates below 2%. But parallel developments in American laboratories were created solutions to both problems. The first breakthrough emerged from MIT's Radiation Laboratory, established in December 1940 to develop microwave radar technology. British scientists visiting America through the TISAD mission in September 1940 had revealed their development of the cavity magnetron, a device that generated powerful microwave radio signals suitable for detecting aircraft and ships with unprecedented accuracy. Dr. Vannevar Bush, heading the National Defense Research Committee, immediately grasped the military implications. Radar could see through darkness, clouds, and smoke. It could measure range and bearing with precision impossible for human observers using optical instruments. The challenge was creating radar systems accurate enough and automatic enough to control artillery fire in real time against fast-moving targets. The solution required solving multiple technical problems simultaneously. Radar needed sufficient resolution to track individual aircraft among formations. It needed automatic target following that did not require constant manual adjustment. It needed accuracy measured in fractions of a degree. And it needed to translate detected positions into firing solutions fast enough to engage targets that crossed the radar's field of view in seconds. Bell Telephone Laboratories began developing an analog fire control computer in December 1940 under Dr. David Parkinson and Dr. Clarence Lovell. Their M9 gun director would continuously calculate trigonometric firing solutions for anti-aircraft weapons, accounting for shell velocity, target speed and altitude, wind drift, air density, powder temperature, and dozens of other variables that affected whether a shell would intersect an aircraft's flight path. The computer used electrical inputs rather than mechanical linkages, allowing it to process radar data automatically and send corrected aiming instructions directly to gun mounts. 490mm anti-aircraft guns could be controlled simultaneously by a single M9 director. The crews would simply load ammunition while electricity aimed their weapons with precision no human could achieve manually. The breakthrough radar came from MIT's Radiation Laboratory. The SCR-584 was designed from its inception as a gun-laying system capable of automatically tracking aircraft through three-dimensional space. It used conical scanning, a technique where the radar beam rotated continuously around the antenna's central axis to maintain precise lock on a target's position. The system achieved angular accuracy of 0.0 to 6 degrees, roughly 1 mil, sufficient to place shells within lethal range of aircraft. More importantly, once locked onto a target, the SCR-584 tracked automatically, continuously feeding updated position data to the M9 director without requiring operator intervention. Range accuracy reached 75 feet at distances up to 40 miles. A prototype M9 director reached the Army just days after Pearl Harbor. Testing revealed extraordinary potential. The analog computer solved firing equations continuously, updating solutions 30 times per second based on radar tracking data. It accounted for the predicted future position of the target, the time of flight for shells, atmospheric conditions, and even the Earth's rotation for long-range engagements. The complete SCR-584 radar and M9 director system demonstrated full functionality on April 1, 1942. The Army ordered 1,200 systems the following day. Production began immediately at facilities across the United States. Bell Laboratories manufactured the M9 directors. MIT's Radiation Laboratory coordinated radar production. By late 1943, the first units were ready for field deployment. The third element of this revolutionary system was already in production. Dr. Merle Tuvey's proximity fuse program had solved the problem of creating miniature radar sets that fit inside artillery shells and detonated automatically when aircraft came within 70 feet. Combined with radar gun laying and automatic fire control, proximity fuses transformed near misses into certain kills. The mathematics became brutally elegant. Traditional anti-aircraft gunnery required visually spotting the target, manually calculating lead angles, setting mechanical time fuses, and hoping every assumption remained valid for the 4 seconds the shell took to reach altitude. The SCR-584, M9, and proximity fuse combination eliminated human limitations from the equation. Radar saw targets in complete darkness at ranges where human eyes saw nothing. The M9 director calculated firing solutions faster and more accurately than any manual method. Proximity fuses eliminated timing errors by sensing the target's actual position and detonating at the optimal moment. Together, these three technologies allowed American gunners to fire blind with greater accuracy than earlier systems achieved while aiming manually at visible targets. But the true revolutionary capability would only become apparent when these systems faced their first real combat test on a confined beachhead, where German aircraft attacked relentlessly and traditional defenses had proven inadequate. The Anzio landings in January 1944 created exactly the desperate circumstances that would validate the new technology's effectiveness. Allied forces had landed at Anzio on Italy's western coast on January 22nd, establishing a beachhead behind German defensive lines with the goal of outflanking enemy positions blocking the advance on Rome. The operation quickly stalled as German forces contained the beachhead and subjected it to sustained artillery bombardment and aerial attack. The narrow confines of Anzio meant American forces could not disperse. Ships crowded the harbour, ammunition dumps, supply depots, and troop concentrations clustered in easily targeted locations. German artillery pounded the beachhead daily. More dangerous were the Luftwaffe night attacks that conventional anti-aircraft fire could not effectively counter. German bomber crews had learned that darkness protected them from visual gun-laying systems. They attacked at night, at dawn, at dusk, any time optical rangefinders struggled to acquire targets. American gunners fired desperately using mechanical time fuses set according to estimated altitudes, watching their shells explode harmlessly while German bombs fell on ships and shore installations. Casualties mounted. The USS Samuel Chase took bomb damage. Supply ships burned at their moorings. German Junkers 88 and Heinkel bombers returned night after night, confident that American anti-aircraft fire posed minimal threat in darkness. Hit rates remained below 2%. The mathematics were unsustainable. At this rate, German air power would eventually strangle the beachhead. In mid-February 1944, the first SCR-584 radars and M9 directors arrived at Anzio. 4 90mm guns were connected to the new system. Crews received hasty training on equipment most had never seen before. The radar operators learned to acquire targets on their circular displays, lock the automatic tracking, and let the machines do work that humans had previously attempted manually. Gunners trained on the fundamentally different procedures required for radar-directed fire. They would not see their targets. They would not manually train their guns. They would simply load ammunition and fire when electrical circuits closed automatically based on radar tracking and computer calculations. Everything about this contradicted their training and instincts. Artillery was supposed to be aimed. You were supposed to see what you were shooting at. The night of February 24th forced them to trust the machines. 12 German aircraft approached Anzio at 8,000 feet under complete darkness. No moon, no stars, visible through overcast. The kind of night when traditional anti-aircraft fire was nearly useless because gunners could not visually acquire targets or observe where their shells burst to correct aim. The SCR-584 operator watched his scope as 12 distinct targets appeared, approaching from the northeast. He selected the lead aircraft and engaged automatic tracking. The radar locked on, its conical scanning beam following the bomber's movements with mechanical precision. Range, bearing, altitude, and velocity data flowed electrically to the M9 director. The analog computer solved the firing equations in milliseconds. It calculated where the target would be when shells reached 8,000 feet altitude. It accounted for wind, air density, projectile ballistics, and target movement. It sent aiming commands through electrical cables to servo motors on the 90mm guns. The barrels swung and elevated automatically. The first salvo fired at 23:17 hours. Proximity-fused shells climbed through the darkness, their miniature radar sets active, searching for the electromagnetic signature of aluminum aircraft. 5 shells detonated within 70 feet of the lead Junkers 88. The aircraft disintegrated instantly. Flaming debris tumbled into the Mediterranean. The remaining German bombers broke formation immediately. Pilots, accustomed to attacking Anzio with near impunity, suddenly faced devastatingly accurate fire from invisible sources. They could not see the radar beam tracking them. They could not evade automatic gun-laying systems that adjusted faster than human operators. Within minutes, 4 more aircraft fell to radar-directed fire. The German formation abandoned its attack run. Surviving bombers scattered and fled. The entire engagement lasted less than 5 minutes. American gunners, who had struggled for weeks to hit anything at night, had just destroyed 5 aircraft on their first attempt with the new system, not by seeing better, but by letting machines see for them. The results shocked everyone who examined the engagement reports. 5 confirmed kills with approximately 60 shells fired. A 12-to-1 hit rate that exceeded anything achieved with conventional fire control methods. More significantly, the engagement demonstrated that American anti-aircraft artillery no longer required visual observation to achieve devastating accuracy. German night attacks on Anzio declined dramatically after February 24. Luftwaffe crews reported encountering impossibly accurate defensive fire that seemed to track them through complete darkness. Intelligence analysts correctly deduced that Americans had deployed some form of radar fire control, but they lacked sufficient technical detail to develop effective countermeasures. The tactical transformation was immediate. American forces at Anzio could now defend themselves effectively, regardless of visibility conditions. Darkness no longer protected attacking aircraft. Clouds and smoke did not blind radar the way they blinded optical rangefinders. The SCR-584 continued tracking targets through weather that rendered traditional gunlaying useless. Additional radar systems deployed to Anzio throughout March 1944. As German commanders learned that night bombing had become suicidal, they shifted to high-altitude daylight attacks that reduced bombing accuracy but improved survival rates. Even in daylight, radar-directed fire proved superior to optical methods for tracking targets through the clutter and confusion of aerial combat. The success at Anzio triggered urgent demand for SCR-584 radars across all theaters. Production accelerated. By D-Day in June 1944, radar-directed anti-aircraft batteries were standard equipment for any American force, expecting significant air attack. The systems deployed to England in preparation for countering the German V-1 flying bomb campaign that began shortly after the Normandy landings. The V-1 presented unique challenges for defensive systems. The pilotless flying bombs travelled at 400 miles per hour at altitudes between 1,000 and 3,000 feet. Too fast and low for effective fighter interception. Too small and agile for conventional anti-aircraft fire that achieved hit rates of only 17% during the first weeks of the V-1 campaign. German launch sites in occupied France fired hundreds of V-1s at London daily. The cruise missiles followed predictable flight paths and maintained constant speeds, making them theoretically ideal targets. But traditional gun-laying systems struggled to track the small, fast-moving weapons. Mechanical time fuses required perfect range estimation and timing. Miss by a fraction of a second and the V-1 flew through empty bursts, unharmed. SCR-584 radars rushed to British anti-aircraft batteries defending London in June 1944 changed the equation fundamentally. The radar's accuracy was actually better suited to tracking V-1s than conventional aircraft because the flying bombs maintained steady courses without evasive maneuvering. Automatic tracking locked onto the missiles easily. The M9 director calculated precise firing solutions. Combined with proximity fuses, the system achieved extraordinary results. Within 6 weeks of deploying radar-directed fire control, British success rates against V-1s jumped from 17% to 74%. On August 28, 1944, German forces launched 104 V-1s at London. Radar-directed anti-aircraft batteries destroyed 64. Fighters accounted for 14. Only 4 reached the city. The improvement represented more than better technology. It demonstrated that artillery could function effectively against targets moving too fast for human reactions. The SCR-584 tracked at 600 miles per hour. The M9 director updated firing solutions 30 times per second. Together, they engaged targets that simply outflew human capabilities. By autumn 1944, American factories were producing radar fire control systems faster than crews could be trained to operate them. The Army established specialized radar operator schools. Gunnery doctrine was rewritten to accommodate automated fire control. Traditional methods, emphasizing visual observation and manual calculation, gave way to procedures where radar operators and computer technicians played roles as important as the gunners themselves. The statistical transformation was undeniable. Anti-aircraft batteries equipped with SCR-584 radars and M9 directors achieved hit rates 3 to 5 times higher than conventional systems. They engaged targets in darkness, through clouds, and in conditions where optical methods were completely useless. Most significantly, they fired blind with greater accuracy than systems that aimed visually at visible targets. But the true revolution was not merely technological. It represented a fundamental shift in how humans and machines worked together in combat. For the first time in history, artillery effectiveness depended primarily on electronic systems rather than human observation. Gunners fired at targets they never saw, trusting calculations performed by analog computers based on information from radio waves they could not perceive. The psychological adjustment proved as challenging as the technical training. Artillery had always been about seeing targets, observing impacts, correcting aim based on where shells fell. Blind fire eliminated that entire process. You fired where the machine told you to fire. You trusted that invisible radio beams were tracking the target accurately. You believed that electrical computers were calculating trajectories correctly. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Veteran gunners struggled with this abstraction. They wanted to see what they were shooting at. They wanted to observe their shells exploding and make corrections based on what their eyes showed them. Radar fire control removed humans from that decision loop entirely. The machines saw, calculated, and aimed. Human crews merely loaded ammunition and maintained equipment. Yet the results spoke for themselves. Batteries equipped with radar fire control destroyed targets at unprecedented rates. They engaged aircraft that conventional systems missed entirely. They protected Allied forces from air attack with effectiveness impossible using traditional methods. The machines were simply better at this task than humans were. The success of blind fire in the anti-aircraft role raised an obvious question among artillery commanders. If radar could track aircraft and direct guns in 3 dimensions, could similar systems help artillery hit ground targets they could not see? The question became urgent as Allied forces advanced across France after D-Day and faced concentrated German artillery fire that traditional counter-battery methods struggled to suppress effectively. Counter-battery fire, the practice of destroying enemy artillery that was shelling friendly positions, had always depended on skilled observers spotting muzzle flashes or using sound-ranging equipment to triangulate gun positions. Both methods worked but required time and favorable conditions. By the time friendly artillery received coordinates and fired, German batteries had often displaced to new positions. The SCR-584 radar operators at the front lines in France during summer 1944 noticed something unexpected. They could see artillery shells in flight on their radar screens. The shells appeared as small, bright blips traveling in parabolic arcs. If radar could track shells, it could potentially trace their trajectories back to determine where they had been fired from. The mathematics proved more complex than for anti-aircraft work. Aircraft flew relatively straight trajectories. Artillery shells followed ballistic curves affected by gravity, air resistance, wind, and dozens of other variables. But mortars fired at high angles created nearly parabolic trajectories that could be calculated if the radar observed 2 points on the shell's upward flight. Experiments began in late 1944. SCR-584 operators attempted to track German mortar bombs shortly after they were fired. If they could capture the bomb's position and velocity while it climbed toward its apex, simple mathematics could extend that trajectory backward to estimate the firing position. The technique worked surprisingly well for mortars whose high arcing flights crossed the radar beam for several seconds. By early 1945, specialized radar operators were assigned counter-battery duties, tracking German mortar fire and calculating firing positions accurate enough for American artillery to engage. The response times were extraordinary. German mortars would fire, radar would track the bombs, calculations would identify the firing position. American artillery would receive coordinates and fire counter-battery missions. the entire sequence often completed before the German mortar bombs even reached their targets. German mortar crews reported devastating accurate counterfire arriving within minutes of their opening fire. Units that had previously fired multiple salvos from single positions found themselves under immediate attack. The only effective response was shoot-and-scoot tactics, firing just a few rounds and immediately displacing. This reduced the effectiveness of German indirect fire significantly. The success with mortar tracking led to attempts at tracking larger artillery shells. This proved more difficult because howitzer shells travelled at lower angles and higher velocities. But under ideal conditions, with the radar positioned properly and the target battery firing at high angles, the SCR-584 could sometimes track shells and generate rough firing position estimates. The techniques developed for anti-aircraft radar fire control found parallel application in naval warfare, where the challenge was not tracking fast-moving aircraft but engaging enemy ships beyond visual range or in darkness. American battleships and cruisers faced the same fundamental problem as anti-aircraft batteries. How do you hit targets you cannot see? The answer emerged from different technology but similar principles. Naval fire control radar could measure range and bearing to enemy vessels, with accuracy impossible for optical rangefinders, particularly at night or in poor visibility. When combined with sophisticated analog fire, control computers, radar-equipped ships could engage targets in complete darkness with devastating effect. The night of November 14th to 15th, 1942, off Guadalcanal, in the Solomon Islands, provided the defining test of naval radar fire control. American battleship USS Washington, under Rear Admiral Willis Lee, faced a desperate tactical situation. Japanese Admiral Nobutake Kondo commanded a bombardment force, including battleship Kirishima, heavy cruisers Atago and Takao, and numerous destroyers, all approaching Guadalcanal to shell Henderson Field under cover of darkness. Lee's force had been reduced to just Washington and battleship South Dakota after Japanese destroyers savaged his screening destroyers in the opening phase of the engagement. South Dakota then suffered catastrophic electrical failures that knocked out her radar, fire control systems, and most gun batteries. The ship became effectively blind and unable to fight, silhouetted by burning American destroyers. Washington alone stood between the Japanese bombardment force and Guadalcanal. Admiral Lee possessed one crucial advantage. Washington carried the Mark III fire control radar, a system capable of detecting enemy ships at ranges beyond 20,000 yards and tracking them automatically, even while Washington maneuvered. The radar fed range and bearing data directly to the ship's Mark VIII fire control computer, which calculated firing solutions for the 9 16-inch guns in Washington's main battery. Japanese forces had detected and were attacking South Dakota, apparently believing they had defeated the American force. Washington remained undetected in the darkness, her SG surface search radar tracking multiple Japanese ships while her fire control systems prepared engagement solutions. At 11:16, Washington's radar locked onto Kirishima at 8,400 yards. The range was astonishingly close for battleship combat. At that distance, 16-inch shells would arrive in seconds. Fire control solutions were calculated and sent to the gun turrets. The barrels trained and elevated automatically based on radar tracking data and computer calculations. Not a single American observer could see Kirishima through the darkness. Washington was preparing to fire blind at a target visible only as bright blips on radar screens. At 11:17, Washington opened fire. 9 16-inch shells, each weighing 2,700 pounds, crossed the darkness in a single devastating salvo. The shells hit Kirishima's superstructure and punctured her hull below the waterline. A second salvo followed 20 seconds later, then a third. Washington's gun crews loaded and fired with mechanical precision, while radar tracked the target and computers aimed the guns. Over 7 minutes, Washington fired 75 16-inch shells and over 400 5-inch rounds at Kirishima and surrounding Japanese vessels. The battleship's fire was devastatingly accurate despite complete darkness and the chaos of surface combat. Radar tracking allowed Washington to maintain fire on targets that optical rangefinders would have lost immediately in the night and smoke. Hiroshima suffered catastrophic damage. At least 9 16-inch shells and 45-inch shells struck home, wrecking her superstructure, setting fires, and flooding compartments. Her steering jammed. Power systems failed. By midnight, she was circling helplessly, her ability to fight effectively destroyed. Japanese forces abandoned the bombardment mission and withdrew. Hiroshima was scuttled the following morning. Washington had achieved what conventional night gunnery considered nearly impossible. She had engaged and destroyed a battleship in complete darkness through radar-directed fire control, scoring hits at rates that exceeded most daylight engagements using optical rangefinding. The engagement demonstrated that radar fire control gave American naval forces decisive advantages in night combat, where Japanese optical superiority became irrelevant. Admiral Lee's report emphasized the radar's capability. Washington had tracked and engaged targets invisible to human observers. The Mark 8 fire control computer had calculated firing solutions faster and more accurately than manual methods. Most significantly, the engagement proved that blind fire was not merely effective, but actually superior to traditional visual gunnery in darkness. The implications rippled through American naval doctrine. Night surface combat had traditionally favored the Japanese, whose excellent optical rangefinders and aggressive tactics won decisive victories at Salvo Island and other early engagements. Radar fire control fundamentally reversed that advantage. American ships could now see and fight effectively in complete darkness, while Japanese forces remained dependent on optical methods that required some visibility. American battleships Iowa and South Dakota-class, cruisers, and even destroyers received increasingly capable fire control radars throughout 1943 and 44. The systems evolved rapidly. Later radars could track multiple targets simultaneously. Fire control computers became more sophisticated, accounting for increasingly complex ballistic variables. Integration between radar, computer, and gun mounts became more seamless. By 1944, American warships routinely engaged targets beyond visual range in darkness or through smoke and weather. The ability to fire blind had become standard operating capability rather than experimental technology. Japanese forces adapted by avoiding night surface engagements where possible, recognizing they could not compete against American radar fire control. The parallel development of anti-aircraft and naval radar fire control revealed common principles. Both eliminated human limitations from targeting problems where speed, distance, or visibility exceeded human capabilities. Both relied on radar to see what humans could not perceive. Both used analog computers to calculate solutions faster than manual methods. Both allowed blind fire with greater accuracy than visual aiming. The true integration of these technologies came when all elements operated together in combined operations. By late 1944, American task forces included ships with naval radar fire control for surface combat, anti-aircraft batteries with SCR-584 radars and M9 directors, and proximity fuse ammunition. The combination created defensive capabilities unprecedented in naval warfare. Enemy aircraft approaching American task forces faced multiple overlapping detection and engagement systems. Surface search radars detected them at extreme range. Air search radars tracked them as they closed. SCR-584 fire control radars locked onto them automatically. M9 directors calculated firing solutions. Proximity fuses ensured shells detonated at optimal range. The entire sequence operated faster than human reaction times. Enemy surface ships faced similar comprehensive detection and engagement. Surface search radars found them beyond visual range. Fire control radars tracked them through darkness and weather. Analog computers calculated firing solutions. Main battery guns fired automatically at targets crews never saw. The result was American naval forces that could fight effectively, regardless of visibility conditions or time of day. The statistical evidence was overwhelming. American ships equipped with radar fire control achieved hit rates 3 to 5 times higher than vessels using optical methods. They engaged targets in conditions where traditional gunnery was impossible. They protected themselves against air and surface threats with effectiveness that earlier in the war would have seemed miraculous. But the technology required fundamental changes in naval training and doctrine. Radar operators became as critical as gun captains. Electronics technicians maintained equipment that determined whether ships could fight effectively. Traditional skills like visual spotting and mechanical range estimation remained important but secondary to radar and computer operations. Young sailors trained on equipment that had not existed when the war began. They learned to read radar displays, interpret electronic signals, trust machine calculations over human judgment. The change was profound. Naval gunnery had always been about seeing targets through powerful optics, observing shell splashes, correcting aim based on visual feedback. Radar fire control abstracted all of that into electronic signals and automatic calculations. Veteran officers struggled with the transition. They had spent careers developing visual gunnery skills that radar made largely obsolete. They understood rangefinders and plotting boards. Electronic fire control seemed like black magic. You fired at blips on a screen and trusted that shells would hit targets you never saw. It contradicted everything their experience taught them about naval combat, yet combat results forced acceptance. Ships with radar fire control won engagements. Ships without it lost. The Battle of Guadalcanal demonstrated this brutally. Washington, with functioning radar, destroyed Kirishima. South Dakota, blind after electrical failures, took devastating damage from Japanese forces who could see her silhouetted against burning destroyers. The difference was not courage or skill, but technology that allowed one ship to see and fight in darkness, while the other could not. By 1945, blind fire had become so standard that younger officers and sailors could not imagine naval combat without radar. To them, firing at targets beyond visual range or in darkness was normal procedure, not revolutionary innovation. The technology had been absorbed so thoroughly into operations that its radical nature became invisible. The ground forces experienced parallel transformation. Artillery battalions that received radar-capable counter-battery systems in late 1944 operated fundamentally differently than units relying on traditional observation methods. They engaged enemy artillery positions within minutes of detecting fire, often before spotters could report coordinates. German commanders noted the devastating speed of American counter-battery fire and issued orders to minimize time spent in firing positions. The integration of anti-aircraft, naval, and ground artillery radar fire control created comprehensive American technological superiority in indirect fire. Whether engaging aircraft, ships, or enemy artillery positions, American forces could detect, track, and engage targets faster and more accurately than opponents who relied primarily on visual observation. This advantage compounded through the war's final year. As American industry produced radar systems in massive quantities, more units received equipment that made blind fire possible. Training programs taught thousands of radar operators and fire control technicians. Doctrine evolved to exploit radar capabilities fully. By the time Germany surrendered in May 1945, American artillery operated with capabilities that would have seemed impossible 4 years earlier. The Japanese experience in the Pacific reinforced the lesson. American naval forces with comprehensive radar fire control dominated surface engagements and defended effectively against air attack. The Battle of the Philippine Sea, in June 1944, saw American ships equipped with radar fire control and proximity fuses destroy over 400 Japanese aircraft while suffering minimal damage themselves. Japanese pilots reported impossibly accurate defensive fire that made coordinated attacks suicidal. The technological advantage was not subtle. American forces could fight effectively in conditions where their opponents were significantly impaired. Darkness did not blind American ships and anti-aircraft batteries the way it blinded Japanese forces lacking equivalent radar. Poor visibility that hampered visual observation barely affected radar systems. The ability to fire blind with precision created asymmetric advantages that determined battle outcomes. The post-war analysis quantified what combat experience had demonstrated. Anti-aircraft batteries with SCR-584 radar and proximity fuses achieved kill rates 5 to 10 times higher than conventional systems. Naval vessels with fire control radar scored hits at night at rates approaching daylight optical gunnery performance. Counter-battery radar reduced the time required to locate and engage enemy artillery from hours to minutes. The human cost of this technological superiority appeared in casualty statistics. American ships survived air attacks that would have sunk them earlier in the war. Ground forces faced less effective enemy artillery fire because counter-battery operations neutralized German guns rapidly. Aircraft casualties declined as improved anti-aircraft defenses made enemy airspace increasingly lethal. The machines that allowed blind fire saved American lives by destroying threats more efficiently. Yet the technology's significance extended beyond its immediate military effectiveness. Radar fire control represented a fundamental shift in how humans and machines collaborated in combat. Previous weapons augmented human capabilities but remained under direct human control. A rifle extended your reach, but you aimed it. A cannon multiplied your strength, but you calculated its trajectory. Artillery shells exploded when you set them to explode. Radar fire control transferred critical decisions to machines. Radar decided what was a target and what was clutter. Computers calculated where to aim. Automatic systems fired guns when solutions were optimal. Proximity fuses decided when to detonate. Human operators monitored and guided these processes but did not control them in real time. The machines operated faster than human reaction speeds allowed. This partnership between human and machine became the template for modern warfare. Post-war fire control systems evolved into increasingly sophisticated automated systems. The analog computers of World War II gave way to digital computers. Mechanical radar antennas became phased arrays. But the fundamental principle remained constant. Machines handle tasks requiring speed and precision beyond human capabilities, while humans provide judgment and oversight. The soldiers and sailors who operated the first radar fire control systems pioneered this collaboration without fully understanding its implications. They learned to trust machines to see targets they could not perceive. They accepted that computers calculated faster than manual methods. They fired at coordinates displayed on screens rather than targets visible through optics. In doing so, they demonstrated that humans could work effectively with automated systems in combat's chaotic environment. The German and Japanese forces, who faced radar-directed fire, could not understand what had changed. They saw shells exploding with supernatural accuracy in darkness. They experienced counter-battery fire arriving impossibly quickly. They watched aircraft fall to anti-aircraft fire that seemed to anticipate every movement. Without equivalent technology, they could not comprehend how American forces achieved such precision. Some German intelligence reports correctly identified radar as the enabling technology. They noted that American ships and anti-aircraft batteries performed best in conditions where radar had clear advantage over optical observation. But understanding the problem did not provide solutions. Germany lacked the industrial capacity and electronics expertise to develop equivalent systems at scale. Japan's electronics industry was even less capable of matching American radar technology. The result was American forces that could fight effectively day or night, in clear weather or clouds, against visible targets or targets beyond visual range. The ability to fire blind with precision transformed every type of engagement, from anti-aircraft defense to naval surface combat to counter-battery artillery. It represented perhaps the single most significant American technological advantage of the war's final 2 years. The soldiers who witnessed this transformation understood they were seeing something historically significant: artillery that hit targets no human eye could see, ships that fought in complete darkness with daylight accuracy, anti-aircraft fire that destroyed aircraft through clouds. These capabilities redefined what was possible in combat, creating expectations that would shape military technology development for generations. The engineers and scientists who created radar fire control systems worked urgently under wartime pressure, solving immediate tactical problems without time to contemplate broader implications. Dr. Vannevar Bush coordinating radar development. The scientists at MIT's Radiation Laboratory designing the SCR-584, Bell Labs engineers creating the M9 Director, Dr. Merle Tuve developing proximity fuses. Each solved specific technical challenges. Together they created integrated systems that allowed blind fire with unprecedented precision. The industrial achievement was equally remarkable. American factories mass-produced sophisticated electronic systems at scales previously considered impossible. The SCR-584 alone required precision manufacturing of hundreds of components. 1,200 complete systems were built. Thousands of M9 directors were manufactured. Millions of proximity fuses were produced. The industrial mobilization necessary to field these technologies at scale represented American manufacturing capacity operating at full capability. By war's end, the ability to fire blind had become so standard in American forces that its absence would have been crippling. Officers planned operations assuming radar fire control would be available. Tactics incorporated the ability to fight effectively in darkness or poor visibility. Training programs taught radar operation as fundamental skill. The technology had been absorbed completely into military operations. The legacy extended far beyond World War II. Every modern fire control system descends from the radar-directed systems developed between 1940 and 1945. Surface-to-air missiles use descendants of the SCR-584 tracking algorithms. Naval fire control systems evolved from Mark III and Mark VIII radar. Counter-battery radar traces lineage to the wartime experiments, tracking mortar bombs and artillery shells. The principle of using sensors and computers to enable engagement of targets beyond human perception became foundational to modern warfare. Precision-guided munitions, beyond visual range missiles, automated target tracking, fire-and-forget weapons, all build on the concept pioneered in World War II. Machines see what humans cannot. Computers calculate faster than manual methods. Automated systems engage targets before human reactions are possible. The soldiers and sailors of 1944 and 45 who first trusted machines to aim their weapons created a model for human-machine collaboration that defined subsequent military technology. They demonstrated that humans could work effectively with automated systems in combat. They showed that transferring time-critical decisions to machines produced superior results. They proved that blind fire directed by electronics could exceed the accuracy of visual aiming by human gunners. The German and Japanese forces who faced this technology recognized they were confronting something fundamentally new. This was not merely better equipment. It represented a different approach to warfare where electronics and automation played roles previously reserved for human observation and calculation. Their inability to develop equivalent systems contributed directly to their defeat. The American technological advantage in radar fire control exemplified how industrial capacity, scientific expertise, and engineering innovation could create decisive military capabilities. The systems that allowed blind fire emerged from coordinated efforts across universities, laboratories, and factories. They required unprecedented integration of radar, computing, and weapons systems. They demonstrated that complex technical problems could be solved rapidly when sufficient resources and talent were mobilized. 4 years after Pearl Harbor, American artillery, anti-aircraft guns, and naval weapons routinely engaged targets their crews never saw. They fired through darkness, clouds, smoke, and at ranges beyond human vision. They hit with accuracy that earlier generations would have considered impossible. The mathematics that seemed terrifying in 1940, when 20,000 shells were required to down a single aircraft, had been transformed. Radar fire control achieved kill rates exceeding 50% against the most challenging targets. The young physicist at MIT who designed radar circuits, the Bell Labs engineer who programmed analog computers, the factory worker who assembled fire control equipment, the radar operator who tracked targets on a glowing screen, the gunner who loaded shells without seeing what he was shooting at, each contributed to this transformation. Together they created systems that allowed American forces to fire blind with greater precision than earlier systems achieved while aiming visually at targets in clear daylight. The age of blind fire had arrived completely. What began as desperate experiments to improve anti-aircraft effectiveness became comprehensive capability that transformed every aspect of artillery and naval combat. American forces no longer needed to see their targets to destroy them. They had taught their weapons to see through radio waves and aim through electrical calculations. They had created machines that fought more effectively than human observers could direct. The implications reached far beyond military technology. Radar fire control demonstrated that humans and machines could collaborate on tasks requiring capabilities beyond human limitations. It showed that automated systems could handle time-critical decisions in chaotic environments. It proved that trusting calculations performed by machines could produce results superior to human judgment in specific domains. The soldiers who operated these systems in combat pioneered a relationship between human and machine that would characterize modern warfare. They learned to trust sensors they could not verify. They accepted calculations they could not check manually. They fired at targets they never saw. In doing so, they demonstrated that the future of precision warfare lay not in enhancing human observation, but in creating systems where machines handled tasks humans could not perform. The technology that allowed American gunners to fire blind and hit their targets with devastating accuracy represented more than engineering achievement. It symbolized the transformation of warfare into a domain where electronic systems and automated calculations determined outcomes. The age when human eyes and hands directly controlled weapons was ending. The age of sensors, computers, and automated systems had begun. American forces in World War II pioneered that transition, creating capabilities that defined military technology for generations that followed. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.